Hello everyone, welcome to my talk entitled Sparsity Aware Reachability Computation for Massive Graph. I am Sung-Soo Kim from ETRI. This is joint work with Youngmin Kang from Dongmyeong University and Younggu Kim from Chungnam National University. This is the outline of my talk. Graphs are widely used. Generally, information network represented as a graph are popularly employed in a variety of applications, such as social network, knowledge graph, biomedical network, molecular network, and so on. Even with the popularity of information networks, diffusion analysis on massive graph is still challenging. In particular, most real networks such as knowledge graph and biomedical networks are directed graphs and disconnected graphs. Moreover, these networks in the real world are also massive. Prior research in graph mining found that existing networks manifest surprisingly small diameter, even though graphs are massive. Specifically, despite the huge size of the World Wide Web, the web is highly connected graph with an average diameter of only 19. Furthermore, most social networks also present the 6 degree or 4 degree of separation characteristics. Likewise, most of real networks are sparse. This slide shows two examples of disconnected graphs. The image on the left is the core dataset, which is the citation network. A citation network is a directed graph that describes the citation within a collection of documents. Each vertex in the graph represents a document in the collection, and each edge is directed from one document toward another that it cites, or vice versa, depending on the specific implementation. Most real-world citation networks are directed graph with the directionality. Unfortunately, existing studies have focused on unweighted and connected graphs. The computation of reachability graphs have long been a fundamental operation of graph algorithm. Graph reachability query is to test whether there is a path from a node U to another node V in a large directed graph. Most real-world applications, such as tracing virus diffusion, analysis of traffic congestion propagation, utilize directed graphs. However, most of the existing methods concentrate on undirected graph with limited attention to the directed disconnected network. Inspired by the characteristics of small diameter, directionality, and sparsity of common real networks, we present a novel arbitrary order reachability matrix computation framework for directed disconnected graph. The proposed approach constitutes the following major key benefit. First, we formulate an AORM framework as an arbitrary order reachability matrix computation with the objective of approximating multi-hop similarity among vertices in a graph. Second, AORM works on directed disconnected graphs that are common in real-world networks such as citation networks. Third, one of the key features in our framework is the incremental computation for efficiently approximated reachability and all-pair-shorted-path solution. Lastly, our approach supports space and computational efficiency by using a sparse matrix for processing massive network. Now, let me introduce the proposed framework called AORM. The image on the left shows the notion of arbitrary order reachability on the graph. The path from V0 to V10 has two different paths. One is V0, V8, V9, V10 paths. This path provides the third order reachability. The other is V0, V8, V9, V11, V10 paths. This is the first order reachability. The blue dashed line phase is optimal reachability from V0 to V10. The arbitrary order reachability query problem is to compute the reachability via k-hop among every vertex in a graph as a k-order reachability matrix. Now I'm going to explain the overall architecture of the AORM. To compute arbitrary order reachability, existing method compute the kth power of the adjacency matrix. However, the powers of the adjacency matrix can diverge or produce a large number. To overcome this problem, we exploit the Boolean reachability matrix instead of the adjacent matrix. First, we extract the neighborhood information in adjacent matrix A as an NA. We assign the input adjacency matrix to first order reachability matrix R1. Then we use NA and R1 to compute the second order reachability R2. Likewise, we can compute the third order reachability R3 using NA and R2. Our goal is to compute an arbitrary order reachability matrix, including only the all-pair shortest paths in unweighted, directed, disconnected graphs. To achieve this, we introduce the AORM framework, which performs the fast computation of optimal reachability metrics. In our work, we present three types of AORM algorithm. MAORM exploit SIMD-based matrix multiplication. IAORM utilize an incremental k-order reachability matrix without matrix multiplications. SAORM use a sparse matrix for incremental matrix multiplication for reachability computation. To obtain an optimal reachability matrix, our algorithm deals with removing unimportant works. We call this process reachability pruning. We perform the pruning for the following three types of insignificant works, such as cycles, trails, and longer paths to obtain an optimal reachability matrix. First simple idea is to exploit the SIMD-based matrix multiplication for the power iteration of reachability matrix. This is called MAORM. MAORM receives the adjacency matrix A and the reachability constraints KC as inputs. This algorithm consists of two phases, the initialization phase and the incremental optimal reachability matrix computation phase via matrix multiplication. In the initialization phase, first, the algorithm initializes a hop count variable reachability matrix and footprint matrix. For reachability pruning, the footprint matrix contains a footprint set with the vertices bounded by a vertex vi within a k-step, including vi itself. In the incremental reachability computation phase, it performs k-order optimal reachability matrix computation via the vectorized reachability pruning. To obtain a Boolean reachability matrix, we exploit the Heaviside step function hx. This function returns 1 if x is larger than 0 and 0 if otherwise. And it updates a footprint matrix F. Then it incrementally produces the optimal reachability matrix according to the hop count k. It performs iteratively this procedure until the k-order reachability matrix is converged or reachability constraints are reached. This slide illustrates the key idea of the computation procedure in IEEE. Basic idea is that we can utilize the column-wise summation of non-zero element based on neighborhood information in an adjacency matrix. To overcome the divergence problem for the power of the adjacent matrix, we exploit the Boolean reachability matrix R instead of the adjacent matrix A. We use big V operator to perform the element-wise logical OR operation. With all columns of jth row in Rk-1, where J is the set of the first order neighborhood node of I. This figure shows the detailed IAORM framework. First, IAORM extracts the neighborhood information NA. Then it exploits this information to perform incremental computation for reachability matrices from the order of 1 to k. Our algorithm constructs the ith row of Rk using Na and Rk-1. For reachability pruning, we use footprint matrix F as a mask to reachability matrix. This procedure continues until reachability converged and reachability constraints are satisfied. Now let me explain the IAORM algorithm. IAORM also consists of two phases. In the incremental reachability computation phase, based on neighborhood information NA, the algorithm performs the computation of an optimal reachability matrix with reachability pruning. The pseudocode in the algorithm on the right show how we compute all fair shortest paths using AORM. Here, D denotes all pair shortest path distance matrix. The algorithm incrementally computes the APSP distance matrix according to the reachability constraint. The time complexity of exact APSP is order of NMD, where D denotes the diameter of a graph. Although the MAORM algorithm speeds up reachability computation on small graphs, it still takes a long time to handle massive graph in practice. To overcome this limitation, we introduce a sparse matrix-based approach called SAORM for computing graph reachability. Because graphs in the real world are sparse, we can improve the computational performance by using sparse metrics such as compressed sparse law matrix. The algorithm on the right shows the SAORM algorithm, which utilized sparse metrics for incremental reachability computation. First, to provide space and computational efficiency, it convert from a dense matrix to sparse matrix in the initialization step. Similar to the MAORM algorithm, the incremental procedure is repeated until the matrix is converged or the constraint is met. Now, let me explain the experimental result of our research. In our experiment, we conduct comprehensive experiment on synthetic networks and neural networks. All of experiments are conducted on a single computer to evaluate APSP computation performance. We conducted performance comparison with the following 4 baseline methods, including popular network analysis libraries such as SNAP and NetworkX. In terms of time complexity, Zidell methods is the best APSP algorithm that works on undirected, unweighted, connected graphs. We perform the APSP performance comparison of our three algorithms, such as MAORM, IAORM, and SAORM against the four baselines. We conducted the experiment for 20 synthetic networks and 20 real networks. Most synthetic datasets are connected and undirected networks. 3 datasets were generated from random graph generator exploiting the Network X API, and we exploit 3 disconnected networks and 1 directed network for synthetic dataset experiment. Real-world datasets have 6 different network types, such as citation network, social networks, etc., as shown in the table on the right. In our experimental result of APSP performance comparison, we can see that our proposed method, MAORM and IAORM, outperform 3 baseline for synthetic network generated from different random graph generation models and various types of real-world networks. This table shows another experimental result for APSP performance comparison with the AORM algorithm, snapshot, network X, and vectorized BFS-based APSP. As a result, SAORM provides the best performance on various types of real-world networks. Specifically, SAORM outperformed from 1.7 times to 22.5 times compared to the SNAP network library. We performed the APSP performance comparison between our method and 3 baseline for 10 different random networks based on Barabashi-Albert gross model, as shown in the image on the left. Also, we generated random graphs based on the Barabashi-Albert model with 5 different node sizes. You can see that our approach outperforms SNAP by 3.7 times and Network X by 13 times, as shown in the image on the right. In the experiment for incremental APSP performance, we gradually set reachability constraints based on the network diameter. As a result, you can see that the proposed method is up to 19.2 times faster than the incremental computation of network X, as shown in the image on the right. Note that Seidel method do not support the incremental APSP computation due to its recursive algorithm nature. Also, SNAP does not provide a function for APSP computation by an incremental fashion. We conducted the experiment of incremental APSP computation for the Elder-Stirwanick random graphs. The image on the left, the line plots represent the correctness of approximate solution for graphs with different edge probability. The image on the right shows the difference between the approximate and exact computation of all pair shorted paths. Note that the difference between the exact result and approximate estimation is visualized in black rectangle, and zero value entry are colored as white. You can see that our method provides fast convergence property, finding the exact solution within 4 iterations in this experimental setting. To wrap up, we have proposed the sparsity-aware reachability algorithm, which can provide a fast performance for massive graph via incremental fashion. Our approach supports space and computational efficiency by using a sparse matrix for processing massive networks. Also, the proposed algorithm handles directed and disconnected networks, which are prevalent in real-world networks such as citation network and load network. Moreover, the computational result of the AORM is asymptotically collected and rapidly converged to the exact solution. This is the end of my presentation. Thank you for your attention.